All right, so this is lesson 5 for AP Calculus BC's Unit 1. It's the first one that moves us out of pre-calculus stuff into the stuff that leads to calculus material. And by that I mean it's the first one that deals with, oh, where's my pen? It's the first one that deals with limits. And since this is the first lesson that deals with limits, it's the first one that gets us on our way. Again, we did a lot of limit work last year, so a lot of this stuff is going to be familiar to you. And I want to refamiliarize you with the math we're going to do by putting it in a context. So I want to compare and contrast the idea of average speed over an interval with the idea of instantaneous speed at a particular point. So if I say that I'm looking for the average speed that my car traveled over 3 hours of driving to Albany, I mean that I want to take the total distance that I traveled, which was 180 miles. I want to divide that by the time it took, which is 3 hours, and I want to get an average speed. The car wasn't going 60 miles an hour the whole time, but on average, there it is. Now, the instantaneous speed is what the cop is looking for when he shoots the radar gun at my car. He wants to know at the exact moment that he fires that radar gun, how fast would I travel if I were to travel at that speed long time? That's the idea. So when we talk about average speed is the slope of a secant line to a distance time graph. But instantaneous speed is a slope of a tangent line to a distance time graph. And of course, the problem with using the word slope is that slope is always change in distance over change in time. And with instantaneous speed, that gets weird because there is no change in time. Okay, so if I can demonstrate in the following way. No, I'll do it on that previous slide. Let's suppose that an object falls such that the vertical distance that it travels over time is given by 5t squared at t seconds with y in meters. This is roughly true in the gravitational field of the Earth, roughly true. It's really 4.90330, whatever. But we'll say 5 because it'll be easier for us. I want to talk about the average speed over the first 3 seconds. And then I want to talk about the average speed over the first 4 seconds. And then I want to find the instantaneous speed at time equals 3 seconds. So if I'm looking for average speed is the slope of a secant. It is a change in distance over a change in time. The change in time is given to us. We're looking at the first 3 seconds. If I want to know what the change in distance is, then I have to know, okay, where am I at 3 seconds? That's 5 times 3 squared. Where am I at 0 seconds? That's 5 times 0 squared. And if I work out that computation, that's 45 minus 0 is 15 meters per second. Now, the object wasn't falling at 15 meters per second the whole time, but it fell on average at 15 meters per second. And the same kind of thing is going to happen over the first 4 seconds. We're going to look at where we are at 4 seconds, where we are at 0 seconds, and divide by change in time. We're looking over the first 4 seconds. That runs from time equals 0 to time equals 4, and you can crunch that out. That's 80 minus 0 divided by 4. That is 20 meters per second. If I'm looking at instantaneous speed, that is a whole other ball of wax, because I want to find a slope, but there's only one point. And so here's how we solve the problem. We compute the average speed over the interval that runs from time equals 3 to time equals 3 plus h. And h is going to represent a teeny tiny change in time. And then we let h get smaller and smaller and smaller, and we look at what happens. We're going to find a slope between two times that are very close together, and then we're going to let the two become one in a beautiful ceremony surrounded by family and friends. So when I'm looking for delta y over delta t, the delta y is a change in y values. So I've got to substitute this into here, and then I have to substitute this into here. So let's do that. 5 times 3 plus h squared minus 5 times 3 squared. The change in time is the difference between 3 plus h and 3, and I think I've got that. Well, a little bit of algebra. Let's hear it for everybody's favorite four-letter F word, FOIL. And this simplifies to 30h plus 5h squared over h. Now, the obvious problem with this is, well, as we let h get smaller and smaller and smaller, the numerator gets closer and closer to 0. But don't worry, the denominator also gets closer and closer to 0, and that's not helpful at all. But we can remove a factor of h from everybody. And so we have 30 plus 5h as the slope of the secant between 3 and 3 plus h. Since that is the slope of the secant, we can say, as h gets smaller and smaller and smaller, 5h gets smaller and smaller and smaller, the change in y over the change in time gets closer and closer to 30. And so we say that the instantaneous speed at time equals 3 is 30 meters per second. That's the argument here. We say, okay, I can't do a slope at 1 point. I have to do a slope at 2 points. But I pick those points very close together, and I shrink that interval of time by letting h get closer and closer to 0. And I say the closer h gets to 0, the closer that value, the closer this value gets to 30. And so that is the idea of a limit that we played with last year. So what did that look like for us? Well, picture time. Wow, that's from, you don't want that. Sine x divided by x. Graph. Zoom. What is the limit as x approaches 0 of sine x over x? Well, again, it's this idea that we let h get closer and closer to 0, and we see what happens to the thing. In this case, I'm going to let x get closer and closer to 0 and see what happens to the function as a whole. So I can do a trace. And if I do a trace, there is no value when x is 0. But if I take values that are really close on either side, I find out that, gee whiz, we are getting daggone close to 1. And in fact, we can prove that. We can prove that that limit is 1. That limit involves some pretty sophisticated trigonometry. I can run it by you if you like in the privacy of somewhere else, but it won't happen in this video. The idea I need you to hear is that when we talk about a limit, We are not talking about what happens at x equals 0. We are talking about what happens as x approaches 0, as x gets closer and closer to 0. If it gets infinitesimally close to 0, the y values get closer and closer to 1. In fact, wholes are irrelevant to limit calculations. Let's pretend. Here's 1, here's 3. Whee! Whole. Whee! We still say that the limit as x approaches 1 of f of x is 3. And that's true if there is no value for the function at x equals 1. That's true if the value of the function is somewhere up here. That's true if the value of the function is somewhere down there. That's true if the hole gets plugged up. Because a limit is only concerned about what happens as x gets closer to 1, infinitesimally close to 1, without touching 1. We don't care what happens at x equals 1. We care what happens as x approaches 1. Does that almost make sense? Almost? Hey, consider the following. There's a cute little graph for you. This is the function y equals f of x. And so I would like to consider with you the limit as x approaches 3 of f of x. The limit as x approaches 3 of f of x. Well, as x gets closer and closer to 3 from either side, closer and closer to 3 from either side, it appears that the y values are getting closer and closer to 0. And in fact, that is true. And in fact, we say that the limit as x approaches 3 of f of x is 0. What about the limit as x approaches 2 of f of x? What is that limit? Well, we could argue that as x gets closer and closer to 2 from this side, we're getting closer and closer to 2. But as x gets closer and closer to 2 from this side, we're getting closer to 1. So the question becomes, is it 2? Is it 1? Do we split the difference? Do we say both answers? No, we don't. If there is no one single number that the function approaches as x approaches 2, does not exist. Oh, should have done it this way. Does not exist. The catchphrase in my classroom is, if they don't agree, it's DNE. Because there has to be one number that the function approaches from either side. Now, we do say that the limit as x approaches 2 from the left of f of x, that's this arrow, as x approaches 2 from the negative side. Well, that's easy. That's 2. And the limit as x approaches 2 from the right side of f of x, that's this arrow, because we're approaching 2 from the positive side. And that is 1. But if these two limits don't match, it's DNE. Now, we could find the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. And I think you would agree that if we approach 3 from the left or 3 from the right, we get 0. And so these numbers match, we get that answer. But we only get that answer if these numbers both match. And that almost makes sense to you, I think. Okay, very cool. Hey, one more thing. One more thing. It is called the sandwich theorem, and it is the thing that is going to get play when we come together, I think. If g of x is less than or equal to f of x, is less than or equal to h of x, for all x in some interval containing c except maybe c. And if the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x equals L, then the limit as x approaches c of f of x equals L. Because this is a video, I know that if I move on, you can always hit the pause button. Well, that's refreshing. What the heck does that mean? Well, that means that if I've got some graph, and here's C, and I know I've got g of x on the bottom approaching some like so, where this would be L. And I've got h of x coming like so. Here's h, here's g. If f of x is trapped between g of x and h of x, then f of x, no matter what it does, no matter how it tries, it gets sandwiched to L itself. It gets sandwiched. Well, let me see if I can spell this out. I want the limit as x approaches 0 of x squared sine of 1 over x. Well, here's what I know. I know that x squared times the sine of 1 over x is less than or equal to x squared, because I know that the sine of anything is less than 1, or at most 1. Similarly, I know that x squared sine of 1 over x is greater than or equal to, no, that's not true. It's greater than or equal to negative x squared, because I know that sine of anything is bigger than negative 1. And so I know that since sine of 1 over x is trapped between negative 1 and 1, I know that x squared sine 1 over x is trapped between negative x squared and x squared. So here's the question. As x gets closer and closer to 0, negative x squared goes to 0. I should have gone with red. Here, we'll make this all red. There. Because it's the g function, it's on the bottom. As x gets closer and closer to 0 on this side, x squared gets closer and closer to 0. And so I can say with confidence that because this function is trapped between two others that go to 0, its limit is 0. And that is the cute little ditty that we call the sandwich theorem. And so that is the first thing you are going to ask about when we get together, because you're going to go, oh my gosh, what is that? And I'm going to have a good explanation for you. All right, so that's our learning. That's our new stuff for the day. We'll see you tomorrow.